We often look around at modern life and feel a quiet sense of disappointment. We were promised flying cars and sleek utopian cities, but instead we got endless scrolling feeds and slightly faster Wi-Fi connections. But if you look past the everyday routine and read the current technological headlines, a very different picture emerges. Concepts dreamt up decades ago are crossing over into reality at a staggering pace. Take the communicators from the original 1960s Star Trek. Starfleet officers flipped open gold lids to instantly talk across planets. It was a futuristic idea that directly inspired the hardware engineers who built the physical flip phones of the 1990s. The show also relied heavily on pads, slender digital tablets used to read single reports or diagnostics. By 2010, the first iPad took that fictional concept and compressed entire libraries, video communication, and global mapping into a single piece of glass. During that same era, computing mainframes were massive, room-filling machines that required punch cards to operate. Yet the crew of the Enterprise could simply talk to the air and ask the ship's computer a question. Today, millions of people ask Siri or Alexa to manage their homes without a second thought. This intersection of hardware and software marks a convergence moment. These concepts are moving into the real world because the technical pillars they depend on, compute power, material science, and machine learning, have finally reached the performance levels necessary to support them. For decades, science fiction has treated the flat screen as a temporary limitation. Early 2000s films, most notably Minority Report starring Tom Cruise, popularized the idea of a fully three-dimensional interface controlled entirely by natural hand gestures. That specific vision is now being engineered for the mass market. With the launch of Apple's Vision Pro and its Vision OS system, the physical monitor is removed entirely, offering an infinite spatial canvas that blends digital apps directly into your physical room. Engineering the spatial computer required severe hardware miniaturization. It relies on a unique dual-chip processing design, paired with ultra-high-resolution micro-OLED displays that pack 23 million pixels. But hardware isn't enough. The missing link was software, running advanced machine learning models that track eyes and hands with zero latency. You select a button simply by looking at it and tapping your fingers together. Moving from keyboards and mice to our own eyes and hands removes the physical barrier between the user and the machine. It changes our relationship with digital space, turning computing from a screen we look at into an environment we inhabit. This convergence extends from digital spaces into physical automation. Writers like Isaac Asimov spent the 20th century defining how humanoid robots would operate within our society, setting expectations that engineers have chased ever since. A recent market study by Roland Berger highlights just how close we are to realizing those expectations. Their data suggests that by 2026, humanoid robots will begin to transition from laboratory prototypes into active participants in industrial supply chains. The physical components required to build these machines have recently hit critical milestones. Lithium-ion batteries now offer sufficient energy density to power heavy movement, and 3D sensors provide precise understanding. But the catalyst driving this deployment is Edge AI, allowing robots to process complex environmental data locally, directly on their internal chips. This on-device processing allows the machine to react to physical resistance in real time. It can instantly adjust its grip on an irregular object, or catch its balance if bumped, moving with a fluidity that was impossible just 5 years ago. These companies aren't building humanoids simply to recreate the human form. They are doing it because our entire industrial world, stairs, door handles, narrow warehouse aisles, is built for the human body. A robot shaped like us can autonomously navigate a world designed by us. Beyond robotics, the convergence is moving directly into our neurology. We are seeing rapid acceleration in brain-computer interfaces, or BCIs, systems designed to translate thought into digital action. Rather than relying on invasive open brain surgery, companies like Synchron are taking an endovascular approach. They feed a small, stent-like sensor array through the bloodstream, safely positioning it next to the motor cortex. Other firms use ultra-thin graphene, perfectly conforming to soft brain tissue to capture incredibly high-resolution neural signals. While early research focused heavily on allowing paralyzed patients to move a computer cursor, this dense signal acquisition is pushing the field wider. Clinical trials are now evaluating long-term cortical implants to actively support motor recovery in stroke patients, or to restore natural, thought-driven control over bionic limbs. Pairing microscopic neuromuscular sensors with highly flexible materials creates a reliable link between the nervous system and digital hardware. This allows the brain to communicate directly with bionic systems, turning human intent into digital action. Viewed together, these advancements reveal science fiction's actual function, a shared intergenerational blueprint that gives engineers the specific conceptual targets they need to begin the work. The speed at which we hit those targets is changing. When authors in the 17th century conceptualized space rockets, it took humanity nearly 300 years to gather the necessary physics and metallurgy to actually leave the atmosphere. By the time 19th and 20th century writers like Jules Verne were publishing, the timeline had compressed. Their detailed visions of electric submarines, military aviation, and digital tablets were engineered into existence within a matter of decades. This chart maps the delay between a fictional prediction and real-world invention. The timeline is collapsing. As custom silicon and AI accelerate the design of their successors, the gap between concept and manufactured product has shrunk from centuries to single years. As this timeline approaches zero, the questions we ask ourselves must change. Our primary challenge is no longer figuring out if we possess the technological capability to build the machines of our dreams. The challenge is determining if our laws, our economy, and our ethics are actually prepared to live with them.